In this lesson, we're going to begin diving deep into functions. And today we're going to learn how to write equations for different linear, geometric, and exponential functions, and then how to evaluate for n. So let's look at our first opening exercise. We have a sequence of perfect squares. Now, if you remember from your multiplication chart when you were in elementary school, we had a multiplication chart that looks somewhat like this. And you had little numbers, 1, 1, 2, 2, 3, 3, and so on. The perfect squares were the numbers that were right in the middle of that multiplication chart. So whenever you had to wonder what 1 times 1 was, that answer would go there, 2 times 2. So those are called perfect squares. We have the sequence, essentially, of perfect squares, where our first term has 1, 2 has fourth, and so on. And they are asking us to write a formula for S of n. We essentially have x and y. In all functions, we have y, that is the dependent variable, and x is the independent variable. And basically what that means, if you remember from science, is that our y value depends on what x is. And that's why we call it a dependent variable. When it comes to functions, we don't always use the variables x and y. What we actually use is a lot of n, and instead of y, we use f of n. And basically what this is saying is that the values that are on this column are a function of whatever n is. This is the same thing as saying x and y is depending on the x value. So I just want to make sure that I'm clear about that and you don't get confused over that. So let's go ahead and put this sequence of perfect squares into my table. If you remember when you had to write a rule in 7th grade from a table, and I'm just going to digress here for a minute and give you an example. Let's say you had n and m, and you had to write a rule or a formula for this particular relationship. Well, the process for that essentially is to find how the values in m change from one to the other. And so you would find in here that you would have to add 2, and then you would have to go to the column of x's, or in this case n's, and you would have to see if they also have the same constant addition. And once you figure that out, you can start writing your rule, right? And so in this case it would be 2n, and then you start plugging it in. Let's say I'm going to choose this ordered pair to plug it in, and I'm going to have, well, it's not y anymore, it's going to be 6 equals 2 times 3, and if that's the case, then that's great, your rule is correct. So that's sort of the process that we went through here. Now, when you have to find a rule for an equation that's not necessarily linear, there are a couple things that will happen. The first thing you have to do is figure out how it changed, right? Well, when you first actually have to figure out if there's a pattern. In this case, if it's physically visible, we don't have to go through all of this. We can simply just write the pattern down. To the power of 2 is going to equal f of n, or the value that stands for y, right? So we have 3 to the power of 2, 4, and we actually call that 4 squared, 5 squared. Anything to the power of 2 is squared, right? So what would be the formula for S of n? So S of n, and actually I need to modify this, that's supposed to be S of n, not F of n, would be whatever n is squared. So the way you would write that is simply, instead of saying y equals, you would just write S of n equals n squared. So how would you prove if 169 is a perfect square? Well, if 169 was a perfect square, then that means that 169 would go on this side with the perfect squares on the right side of the table, which would mean that when you plug it in, it would be on the side of the y, or S of n, and you would have a formula that's 169 equals n squared. And so you would just have to solve for n. In this case, when we solve for an exponent, we have to take the root. Because it's a square exponent, we take the square root. And so n would have to be equal to the square root of 169. And you can just grab your calculator. It's 13, so n equals 13. So n 13 would go there. Well, that is basically how to figure out if that is a perfect square. And we would go ahead and do that for 200 and 225. So I want you to pause the video right now and try to do those two problems the way we did exercise number 1. All right, so we had to prove whether or not 200 was a perfect square. And so in this case, we have to substitute for the formula S of n equals n squared, where 200 would be the value for S of n. And then we would have to solve for n squared by taking the root of 200. And in this case, when we take the root of 200, there are no two factors that make up 200 that are the same, right? We can come up with factors 2 and 100, but none that are the same. 200 is not a perfect square. We can do the same with 225, and we can solve by taking the root, and you will see that 15 times 15 are the two factors that make 225. So n would be equal to 15, and so that would be a perfect square. Now let's think about which term is the number 400 in the sequence of perfect squares. We would have to do the same thing that we did in the other problems. We have S of n equals n squared, and we would have to plug in 400 equals n squared. And when we take the root of 400 in your calculator, you'll see that 40 times 40 make up 400. So n is going to be equal to 40. So that means that 40 is going to be the 40th term. So let's look at number 5. It asks us to create a formula for the area a of x centimeters square of a square. So if I have a square and we have the sides that are x centimeters long, we know that in a square all sides are the same. So we know if that side is x, this is x, and this is also x centimeters long. Our formula, we can say that the area of a square is the same as x squared. Now let's look at number 6, as we're looking at 3 different squares. We're trying to solve. We already came up with our formula. We know that our formula is going to be, let me write it down here just for clarity's sake. So what that means is we have the sides of the square that are x, and we have the area as a function of the sides, which means this is a dependent variable, right? There's a relationship here. We can't figure out what the area is unless we know what the sides are of a square. And then our square is going to look something like this. And because they're all squares, all the sides are going to be the same. So let's take a look at this first square. This first square is 3 centimeters. So that means that the sides are 3 centimeters. And if I were to plug in the 3 in here, it would be 3 squares. I'm going to say that it's 10 and a half. Then I just plug in the 10 and a half. For x, it will be 110 2500ths. So that is going to be my area. This one's a little bit easier, even though you feel like it might be a little bit harder just because of the symbol. That symbol means pi, which is essentially, we say 3.14, and it keeps going because it never ends, right? We call that an irrational number. So in this case, if x is pi, then we just substitute, and it's going to be pi r. I could go ahead and multiply it, but it really wouldn't approximate to the answer, so I'd rather just keep it in terms of pi there. It's pi squared. Why don't you try to do 7 and 8 on your own? Go ahead and pause the video. Alright, so let's go to number 7. Now, of course, you have to plug it in. We have a of x equals x squared, and if we plug in the 0, 0 squared is going to be 0. But remember, they ask you, what does a of 0 mean? That means if your area is 0, what does it mean? Actually, this has no physical meaning, because when you think about the word physical, it means I cannot possibly draw a square that is 0 centimeters in length. For number 8, a of negative 10, again, we can find the answer to that, right? Because you will see that a of negative 10 is basically negative 10 squared, which will be 100. But you can't have a square with an integer as negative 10 centimeters. There's no such thing as negative 10 centimeters. We only measure in terms of positive integers or whole numbers. We can't have, a ruler goes from 0 on up. It doesn't go from 0 to the negatives because we can't measure. And that's, the whole idea of absolute value came in, of like, how do we measure the distance? And in distances that are inherently negative, but we can't measure in negative numbers. So that's where absolute value comes in. But we don't have a situation of absolute value here. We have a situation of a square. And so this has also no physical meaning. We can, however, have a square, here's a different color, with square root of 2 as the sides. And in this case, we have square root of 2, which would be square root of 2 times square root of 2 equals square root of 2 squared 2. That does have physical meaning. You can actually have a square root with a square with a side that measures square root of 2 centimeters.